everyone. Welcome to St. Joseph College for Women Autonomous, Vishakhapatnam. Department of Mathematics welcomes you for the online course on real analysis. The first module is Differentiation and Mean Value Theory. I introduce myself S. Venkatalakshmi, Assistant Professor, Department of Mathematics, St. Joseph College for Women Autonomous, Vishakhapatnam. Now I am going to teach learning outcomes of differentiation. First one, find derivatives. Compute derivatives of a function. Second one, apply rules. What are the rules we are applying in differentiation? Use power rule, product rule, quotient rule and chain rule. Third one, analyze functions. Determine behavior of a function using derivatives. Fourth one, solve optimization. Use derivatives to solve optimization problems. Fifth one, model real world. Use derivatives to model real world phenomena. Find the average rate of change. Determine the average rate of change of a function over a given interval. Seventh one, prove function behavior. Prove that a function is increasing or decreasing or constant over a given interval. Locate the critical points. How to identify critical points of a function where the derivative is 0 or undefined. After successfully completion of this course, the student will be able to learn the given function is how to measure the one quantity changes learning to another. For example, velocity as the rate of change of position. And optimization. Optimization in the sense maximum and minimum. It helps to find the highest and lowest points in a function. Which is very useful in real world applications. After, ensure function continuity and differentiability. It helps to check if a function behaves smoothly or hardly. It predicts behavior of a function. Ensure that a function does not behave exactly between 2 points. Supports Rolle's theorem. Acts as a generalization of Rolle's theorem. Now we are going to discuss the content of this unit. Introduction part, definitions, note points, theorems, theorems related problems. Now I am going to teach the definition of differentiation. Derivability of a function at a point. Let S be an aggregate and F is mapping from S to R be a function. Let C belongs to S. First one, limit extends to C minus f of x minus f of c by x minus c exist. Then we say that f is derivable from left at c. The limit is called the left derivative of f at c and it is denoted by L f dash at c. Therefore, limit f dash at c is equal to limit extends to c minus f of x minus f of c by x minus c. Now right hand derivative. Limit extends to c plus f of x minus f of c by x minus c exists. Then we say that f is derivable from right at c. The limit is called the right derivative of f at c and it is denoted by r f dash at c. Therefore, right hand derivative f dash c is equal to limit extends to c minus limit extends to c plus f of x minus f of c by x minus c. Third one, the derivative at a point. Limit extends to c f of x minus f of c by x minus c exists. Then we say that f is derivable at c. The limit is called the derivative of f at c and it is denoted by f dash at c. Therefore, when we say that f is differentiable, f dash at c is equals to limit x tends to c f of x minus f of c by x minus c. Now note point. If f is derivable at c, if and only if left hand derivative at c is equals to right hand derivative at c. Derivability on an interval. F is mapping from closed interval AB tends to R is said to be derivable on closed interval AB if first condition f dash at c exists for each c belongs to open interval a comma b. Right hand derivative at a exist. Left hand derivative at b exist. Then we are going to discuss the problems on derivability. First problem, show that f of x is equals to sin x is derivable at every a belongs to R. Now the solution is the given function f of x is equals to sin x. Let a belongs to R. F dash at a is equals to limit x tends to a f of x minus f of a by x minus a. That is equals to limit x tends to a sin x minus sin a by x minus a. That is equals to limit x tends to a sin c minus sin d. What is the formula sin c minus sin d? 2 cos c plus d by 2 into sin c minus d by 2. So here apply the formula limit x tends to a 2 cos x plus a by 2 sin x minus a by 2 by x minus a. Limit x tends to a 2 cos x plus a by 2 sin x minus a by 2 by x minus a by 2 into 2. Now continuation of the above problem. Limit x tends to a 2 cos x plus a by 2 is equals to cos a. Therefore f dash at x is equals to cos x for all x belongs to R. Therefore f is derivable at a belongs to R. Second problem, prove that f of x is equals to e power x. The given function is an exponential function e power x is derivable at every point in R. Solution is the given function f of x is equals to e power x. Let a belongs to R. So from the definition of derivability, f dash a is equals to limit x tends to a f of x minus f of a by x minus a. That is equals to limit x tends to a. The given function f of x is e power x minus e power a by x minus a. Limit x tends to a. Take out e power a is a common term. Then we get e power x minus a by minus a minus 1 by x minus a. So that e power a get cancelled. Applying the limits will get e power a into 1 is equals to e power a. Therefore f dash x is equals to e power x for all x belongs to R. Therefore f is a derivable at every point in. Next theorem. The theorem statement is if f is mapping from a to b tends to R is derivable at c belongs to closed interval a comma b, then prove that f is continuous at c. Theorem proof. Given that f is derivable at c belongs to closed interval a comma b, now we prove that f is continuous at c, which means the definition of continuous, limit x tends to c, f of x is equals to f of c. If c belongs to open interval a comma b, consider limit x tends to c, f of x minus f of c is equals to limit x tends to c, f of x minus f of c. That is equals to limit x tends to c, f of x minus f of c by x minus c into x minus c. We are multiplying, dividing with x minus c. Limit x tends to c, f of x minus f of c by x minus c. Limit x tends to c, x minus c. We are applying this limit to this and this. We will get f dash c. This entire value is f dash c into this is 0. So 0 into f dash c will become a 0. Therefore, limit x tends to c, f of x is equals to f of c. If c c is equals to a. Consider limit x tends to a plus f of x minus f of a is equals to limit x tends to a plus f of x minus f of a. That is equals to limit x tends to a plus f of x minus f of a by x minus a into x minus a. We are multiplying with x minus a into x dividing x minus a. Limit x tends to a plus f of a minus f of x minus f of a by x minus a. Limit x tends to a plus x minus a. That implies this is nothing but right hand differentiable, which means r f dash a into this is 0. That entire value becomes 0. Therefore, limit x tends to a plus f of x is equals to f of a. Continuation of above theorem. Similarly, if c is equals to b, then limit x tends to b minus f of x is equals to f of b. Therefore, f is differentiable at c belongs to closed interval a comma b, then f is continuous at c. The note point is the converse of this theorem is not true. That is, f is continuous at c, then f need not be differentiable at c. F of x is equals to mod x. We are saying one example for the note. F of x is equals to mod x is continuous at x is equals to 0 but not derivable at x is equals to 0. F is continuous but f is not a derivable at x is equals to 0. Limit x tends to 0 minus f of x is equals to, we are finding left hand limit. Limit x tends to 0 minus f of x is mod x. That is equals to limit x tends to 0. 0 minus h is equals to 0. Limit x tends to 0 plus f of x is equals to limit x tends to 0 plus the given function is mod x. That is equals to limit h tends to 0. 0 plus h. We are getting 0. Therefore, limit x tends to 0 plus f of x is equals to limit x tends to 0 minus f of x. That is equals to f of 0. The f of 0 means mod 0 is nothing but 0. Therefore, f of x is equals to mod x is continuous at x is equals to 0. Now we are finding left derivative at 0. L f dash 0 is equals to limit x tends to 0 minus f of x minus f of 0 by x minus 0. That is equals to limit x tends to 0 minus mod x minus 0 by x minus 0. That is equals to limit x tends to 0 mod 0 minus h by 0 minus h. That is equals to limit h tends to 0 h by minus h. The value is minus 1. Now we are finding right hand derivative. R f dash 0 is equals to limit x tends to 0 plus f of x minus f of 0 by x minus 0. That is equals to limit x tends to 0 plus mod x minus 0 that by x minus 0. Limit h tends to 0 mod 0 plus h by 0 plus h is equals to limit h tends to 0 h by h. The value is 1. Therefore, L f dash 0 is not is equals to R f dash 0 because L f dash 0 we are getting minus 1 and R f dash 0 we are getting 1. So both are not equal. Therefore, f of x is equals to mod x is not a differentiable at x is equals to 0. The converse of above theorem need not be true. The next problem is prove that f of x is equals to mod x minus 1 is not derivable at x is equals to 1. Solution. We are finding left hand derivative and right hand derivative. If both are not equal, then the given f is not a derivable at x is equals to 1. For that we are finding left hand derivative at 1 is equals to limit x tends to 1 minus f of x minus f of 1 by x minus 1. That is equals to limit x tends to 1 minus the given function f of x is mod x minus 1 minus f of 1 the value is 0 by x minus 1. Limit h tends to 0 modulus 1 minus h minus 1 by 1 minus h minus 1. That is equals to limit h tends to 0 h by minus h is equals to minus 1. Now we are finding right hand derivative. R f dash at 1 that is equals to limit x tends to 1 plus f of x minus f of 1 by x minus 1. Limit x tends to 1 plus mod x minus 1 minus 0 by x minus 1. That is equals to limit h tends to 0 modulus 1 plus h minus 1 by 1 plus h minus 1. Plus 1 minus 1 gets cancelled, will get limit h tends to 0 h by h. The value is 1. Therefore, both are not equal. Both are not same, which means not equal. Limit f dash 1 not equals to L f dash 1 not is equals to R f dash 1. Therefore, f of x is equals to mod x minus 1 is not a derivable at x is equals to 1. Now, the next problem is show that f of x is equals to x into sin 1 by x if x not is equals to 0 is continuous but not derivable at x is equals to 0. That is equals to 0. If x is equals to 0, solution given that f of x is equals to x into sin 1 by x if x not is equals to 0, that is equals to this value is 0 if x is equals to 0. Now first we have to prove that f is continuous at x is equals to 0. Now we have to prove that f is continuous at x is equals to 0. That is the definition of continuous. For each epsilon is greater than 0, there exists delta is greater than 0 such that for all x mod x minus 0 less than delta, that implies modulus mod f of x minus f of 0 less than epsilon. To take epsilon is equals to delta, consider modulus f of x minus f of 0 is equals to f of x means x sin 1 by x minus f of 0 means 0. That is equals to modulus x sin 1 by x. So, apply modulus two functions mod x mod sin 1 by x less than or equals to mod x sin 1 by x value is 1 less than delta. That is equals to epsilon. Therefore, f is continuous at x is equals to 0. Now we have to prove that f is not a derivable at x is equals to 0. Now we are finding derivative of f of x. F dash 0 is equals to limit x tends to 0 f of x minus f of 0 by x minus 0. That is equals to limit x tends to 0 x sin 1 by x minus 0 by x minus 0. That is equals to limit x tends to 0 x sin 1 by x by x. That is equals to limit x tends to 0 sin 1 by x. But limit x tends to 0 sin 1 by x does not exist. Therefore, f is not a derivable at x is equals to. Now we are doing the problems f is continuous but not derivable at x. So the given problem is show that f of x is equals to 1x if x 0 less than x less than or equals to 1. X means if x greater than 1 is continuous but not derivable at x is equals to 1. The given function is f of x is equals to 1 if 0 less than or equals to x less than or equals to 1. F of x is equals to x if x is greater than 1. First we have to prove that f is continuous at x is equals to 1. Limit x tends to 1 minus, we are finding left hand limit. Limit x tends to 1 minus f of x is equals to limit x tends to 1 minus f of x means 1. That is equals to 1 constant function, which means the value is 1. Limit x tends to 1 plus f of x is equals to limit x tends to 1 plus f of x means x. That is equals to limit h tends to 0, 1 plus h is equals to 1 and f dash 1 is equals to 1. Therefore, limit x tends to 1 minus f of x is equals to limit x tends to 1 plus f of x is equals to f of 1. Therefore, f is continuous at x is equals to 1. Now we have to prove that f is not a derivable at x is equals to 1. For that we are finding left hand derivative and right hand derivative. If both derivatives are equal, the given function f of x is a derivable. If both the derivatives are not equal, the given function f of x is not a derivable. Now we are proving f is not a derivable at x is equals to 1. Limit f dash 1 is equals to limit x tends to 1 minus f of x minus f of 1 by x minus 1. That is equals to limit x tends to 1 minus 1 minus 1 by x minus 1. That is equals to the value is 0. Similarly we are proving right hand derivative at x is equals to 1. Limit x tends to 1 plus f of x minus f of 1 by x minus 1. That is equals to limit x tends to 1 plus x minus 1 by x minus 1. That is equals to 1. Therefore, limit f dash 1 not is equals to left hand derivative f dash 1 not is equals to right hand derivative f dash 1. These both are not equal. Then f is not a derivable at x is equals to 1. Now we are going to discuss the problem is continuous but not derivable at x is equals to 1, 2. So that the given problem is f of x is equals to mod x minus 1 plus mod x minus 2 is continuous but not derivable at x is equals to 1, 2. Solution: given that f of x is equals to mod x minus 1 plus mod x minus 2, continuous at x is equals to 1. We are proving continuous at x is equals to 1 and continuous at x is equals to 2. So first we are proving continuous at x is equals to 1. Limit x tends to 1 minus f of x is equals to limit x tends to 1 minus the given function is mod x minus 1 plus mod x minus 2. That is equals to applying the limit h tends to 0, 1 minus h minus h plus 1 minus h minus 2. That is equals to limit h tends to 0, minus h plus minus h minus 1. So here the value is plus h minus h get cancelled. The value is plus 1. Limit x tends to 1 plus f of x is equals to limit x tends to 1 plus mod x minus 1 plus mod x minus 2. Now we are proving limit h tends to 0, 1 plus h minus 1 plus 1 plus h minus 2. Limit h tends to 0, modulus h plus modulus h minus 1. The value is 1. Because in modulus always the value minus become a positive value. Negative become a positive. Always modulus means we are taking positive value. Therefore, limit x tends to 1 minus f of x is equals to limit x tends to 1 plus f of x is equals to f of 1. That is equals to the value is 1. Therefore, f is continuous at x is equals to 1. Now we are proving continuous at x is equals to 2. Limit x tends to 2 minus f of x is equals to the given function is limit x tends to 2 minus mod x minus 1 plus mod x minus 2. That is equals to limit h tends to 0, modulus 2 minus h minus 1 plus modulus 2 minus h minus 2. Limit h tends to 0. Here the value is plus 2 minus 2 get cancelled. Then the value is limit h tends to 0, modulus 1 minus h plus modulus minus h. So the value is 1 only. So here limit x tends to 2 plus f of x is equals to limit x tends to 2 plus modulus x minus 1 plus modulus x minus 2. That is equals to limit h tends to 0, modulus 2 plus h minus 1 plus modulus 2 plus h minus 2. That is equals to limit h tends to 0, modulus 1 plus h plus h. The value is 1. Therefore, both are equal. Limit x tends to 2 minus f of x is equals to limit x tends to 2 plus f of x. Therefore, f of 2 is equals to 1. Therefore, f is continuous at x is equals to. Now, we are finding. Thank you.